Are there any questions over anything we've done so far? So before we start just jumping into like the stuff that we're doing today, is there anything over stuff that we've done so far? So let's look. Kind of like what's going to be on your test is what I wanted to look over at right quick. So if I'm looking at the schedule, it looks like, where did we start? Test 5. The quadratic formula, do you think you could just write out the quadratic formula right now? That's what I think is a good practice.
Do you mean the one that's over, that has like a function, fraction, and the square root and everything?
The one with the song, yes, that's it.
Okay.
Write out that thing. Let's try to write out this quadratic formula. That's a good practice right now.
And you're writing the test this time, right, Matt?
Yeah. I'll get that to you pretty quick.
I'm just wanting to make sure.
I know it's coming up pretty quick. 3, 4, 4, 1.
Okay.
So we got to do quadratic formula, quadratic equations, nonlinear functions, and polynomials, which we're getting into today. And then we're going to go into zeros, or real zeros of the polynomials. And a lot of, to be honest, like the real zeros chapter, I feel like I've been hinting and I've been like dancing around like a lot of the stuff that's in that chapter.
I know. I feel like, to me too, it's kind of redundant almost, but
but it's good to have a little repetition, you know.
Oh yeah.
But it's just basically going over the zeros, which are the same as your x-intercepts, which have some sort of relation that relate back to the factors of that thing, right? Is that where the fundamental theorem comes in? Yeah. Or supposed to? I think it's supposed to right after that. I'll have to go back and look where that falls in Roxwald, I think. But we're getting really close to talking about the fundamental theorem of algebra. Do y'all have it written? Do you need more time, I guess is the question.
All good.
Okay.
Sing the song. X equals what? Negative b plus or minus square root d squared minus 4ac. This is all over
2a. Did I get it right? Hold on. Yeah, that's it.
Yeah, you did. Which part of that is the discriminant?
b squared minus 4ac.
Yep, just that, not the radical, not any other part.
It's just a big fancy way to say we want to talk about the thing that's in the square root. That's basically all discriminant means.
And again, make sure that you have that numerator is all over the division bar, because some people were not doing that earlier.
Oh, they didn't extend this thing all the way.
Yeah.
Okay. Yes. This B is over this 2A just like this guy is. So both of those things. There are two different terms, right?
If sometimes we separated them. You're probably not going to like this because it's got a bunch of symbols, but like when we did our work, we would have to separate whatever we got there
with whatever we got there. So I know it's a lot of symbols and nasty, but yeah, definitely both of those things are over that. Okay. So finishing off 4.1, because I'm thinking quadratic formula was this thing. Quadratic equations was just like a whole mix of the problems, I think. Just a whole bunch of different quadratic equations that we solve either through factoring or through square root method, or we do the quadratic formula was the next chapter that we went over. Then
I actually had some people on the last test solve some of those quadratic equations using the quadratic formula, and I gave them credit for it. I mean, you can always solve using the quadratic formula if you don't want to factor.
Quadratic inequalities. So if you see that word, just ignore it. And now we're on what we're doing right now. I think there were a few word problems in that quadratic equation section too. So if we look at this table, I want to look at this table, and it's maybe hard to read on your camera. I don't know how good your sharpness is there. Mine's a little fuzzy. But hopefully what you're doing is you're looking across like this. And we want to know if this is even, odd, or neither. So if we look across here, what do we notice about these values? The signs are really hard to read, those negative signs, at least on this 5. This one's a -5, it's a +5, -56.
They're opposites.
So I hope the first thing you notice is that these are opposites. And if they're opposites, I'm thinking this might be what sort of function or what sort of symmetry? It is probably a opposite gives you starts with the same word. Yep. Starts with the same letter. The word starts with the same letter. That's what I was trying to say. Opposite gives you odd. The other thing we have to check, there's a lot of O's in this check. It's like opposite, odd. The other thing I really have to check to make sure this is odd is this thing right here. So is this an odd function?
Yes.
Yes. Odd check, right? So it has to go through the origin to be odd. So for odds, you want opposite and you want the origin. It's like they all start with the same letter. So if I ask you if it's odd, just go, right? Something like that. I think you'll probably get it. Any questions about this graph or sorry, this table? How to find it off this table? How would evens look?
Same.
They would be the same. Okay. So if we're looking at this table, we want to look at this table. We want to determine whether this table is odd, even, or neither. So what numbers are we looking at on this Y? So hopefully, I hope you're looking here and here, where X is a -1 and a 1. So you might be giving us on this thing. But if you look along here and you look at the positive and negative of the same X value, what do you notice about your Y values?
Yeah, the same.
They're the same. I don't know if it helps you. End with an E. Y'all already said it. If they are the same, then it's even. So the other thing is they didn't give us an intercept. Do we care what the intercept is? If it's
Not for even functions.
Yeah, not for even. It doesn't really matter. So all that matters is that they're the same. So there's like one sort of check you have to do for even. There's two sorts of checks you got to do for odds. So don't forget your origin check when you do your odd, right? Is kind of the name of the game on this one. Okay. Complete that table as an even function. That's a good way. I want to do this twice. I want to do it as even and do it as an odd. You should be able to do it both ways, I think, right? Yeah. So let's do it as an even function first, and let's try it as an odd. What's this? 21 minus 25, 4, 1, and minus 12. 2. If we want to do this as an even function, what am I putting right here in this minus 2?
Minus 12.
Minus 12. How do you know that? Because you're looking across there at the positive 2. So if I want to know what goes in minus 2, I got to look across to the positive 2. And these things, if they are even, they should absolutely be the same. So this is sort of like our approach to this thing. I want to go here now, I think. Positive 3, if I want to know what goes underneath this positive 3, what number do I look at?
-3.
Yeah, and that gives me what number to put in there?
21.
Yep. Perfect blackjack, right? I think blackjack's probably one of the most fair games at a casinos, from what I've heard. A little bit of tangent on that 21, sorry. Okay, number 1. What's going on under number 1?
-25.
With that said, you're not making money off of any game in a casino. The most fair game in a casino is that game you put your dollar bill into and it gives you the 4 quarters back. That's a horrible joke.
Mhm.
It's got the highest expected value out of anything in that casino. If you go into statistics, you can figure out expected values. So the one thing I didn't answer is like, what is this? What is this thing underneath the 0? Sorry, I'm going a little bit tangent on this problem, but what goes underneath the 0? Ooh. Ah.
Hmm.
It doesn't really matter.
It doesn't really matter. You can put any number your heart desires. Let's go with number 9.
Wow.
9836. I don't know. You can put any number in there. It doesn't matter. Okay, so this isn't even. So for evens, even Steven got to be the same, right? Now we want to think about odd. So now if I want to fill this out with an odd, if I want to if I want to know what goes into minus 2,
I would actually start with the 0 because that would at
0.
least get you started at the origin.
0. And so if you say the origin, I think you're saying 0, 0.
Yeah, because at least that kind of would differentiate it
Okay.
to start with.
And then where are you going to go? To 1?
Well, okay, so like if we want to follow the origin, then yeah, I guess we'd start with the smaller numbers to branch off of it.
So where are we going?
Well, to 1, right?
Yeah, okay, to 1. So what are you going to put underneath 1?
Okay, so if it's odd, then we're gonna go positive 25.
Yeah, you're looking across here. You want to negate this thing. So negative 25 is equal to 25. And hopefully, I think this is the pattern you're talking about, looking across that origin like that.
Yeah.
So what am I putting in underneath that negative 2? That's minus 12 over there, by the way. And it's kind of horribly written. My negative is cramming into my number.
Positive 12.
So if this is minus 12, this is positive 12. And the last one, if this is positive 21, this guy got to be a negative 21. Are there any questions about these tables? So if I give you a table and I ask you if it's odd or even, excuse me, do you think you could tell me whether it's odd or even? If it's even, Stevens, they are the same. If it's odd, there's a bunch of, we got to check the origin. We got to check that they're opposites, right? Okay, So now we have a few of those, like I think these are the min-max problems that we were talking about. So we did even and odd symmetries. We talked about how they look like symbolically. We talked about how they look like in a table. We talked about how they look like graphically. So there's like 3 different forms, right? Now we're back to the maxes and mins, the local max, local mins, absolute max, absolute min. The graph shows the temperature readings of a thermometer on a partly cloudy day, X hours past noon. Identify the absolute max and min, interpret each. Ooh, that's a hard. Zoom in on the graph a little bit. I don't know if y'all can hear that squeak toy, but Willie's going to town over there. All right, so where's my absolute max? Where's my absolute min?
So the max I got 5 and like 85. I'm just estimating here.
Yeah, so you got to kind of, okay, so this is where my absolute max is, right?
Yeah.
585. So if I'm asking for the max, I really want just one of those numbers.
Oh. Yeah, I'm confused of when we're supposed to write it as a point or just write the number.
So if I ask for max or min, I'm just looking for a number. Like how high does this function go?
Oh.
What is the highest y value of this function is what it's asking. So the max here would be the 85. That's the thing that's the largest, right? Maybe that might reinforce, like if we ask for max, if I ask you what's the maximum of something, typically I just want one number, right? Identify absolute max and min, interpret each. So my absolute max is 85. It is good that you pulled out this 5 though. I think this will give us something more to interpret. So if we're looking at this, what is this telling me? 5 comma 85. It looks like my 85 is temperature in Fahrenheit. That 5 should be the time in hours past noon. So if I want to go back and interpret this thing, what is this telling me?
At 5 p.m., the temperature is 85 degrees Fahrenheit.
Exactly. And you can also say that this is the max. If you wanted to say that this was the max, that would also be correct, right? So at 5 p.m., the temperature is 85 degrees Fahrenheit. It doesn't go above that. That's the max. What about my absolute min? So going back, looking at this thing. And I hope you're like just kind of ignore this axis for the most part, right? If we're looking for max and min, we're talking about the y value. Just like kind of look kind of like diagonally here, right? At this sort of thing. Where is the lowest that this is going to go? Like this is the highest. If I bring it down to its lowest point, it's going to be where? That's some guesstimating there, right? I guess.
It looks like it's about 65.
65. Yeah, that's fair enough. I'm not trying to make you guesstimate too much, but it's 65 and it looks like maybe like what, an hour and a half? I don't know. It's not a pretty number. Okay, so now I want to go back and interpret this. What does this mean? You got to interpret that, I guess, that 1.5 correctly, right? Because some potential to mess that up.
Yeah. That would be at 1:30. Temperature is 65 degrees.
Exactly. So at 1:30, your temperature is 65 degrees Fahrenheit. And you could say that this is the min temperature. It's not going to go below 65. Man, this sounds like a pretty day between 65 and 85. Okay. So that is the absolute min and max. If they ask you to interpret things, this is the same way we've been interpreting things, right? This is my X quantity, this is my Y quantity, this is my time. Your units, right? This is my temp. They like to give you hours past. Sometimes they like to give you years past this year or something. So you have to be really careful with how they're defining their X variable, especially when they do time sort of things. Identify any local maxes and mins. Oh, they give you like too much information there. Don't consider endpoints. You shouldn't be looking at the endpoints. I'll give you that hint. So anyway, what are we looking at for local maxes?
The peaks.
The peaks. So I'm hoping you can look at peaks. So if I want to identify local maxes, let me grab another paper because I'm running out of room on this one. But local max. What was Goofy's last name? Wasn't his kid named Max? Sorry, that's a bit tangent.
Yes.
I know he was named Max, but I don't remember his last name. Did he have a last name? Maximilian Goofy? Was Goofy his last name?
I think her last name is Goof.
Okay. Okay. Very important to this problem. But let's identify any local maxes. So the local maxes would be what? So we've already talked about this guy is 85. I guess we have to look at this other thing that I put a red dot on. Where is he falling? Like, yeah, it's not pretty. What would y'all say? 78?
78, 79.
Yeah, something like that. Where am I looking? Ooh, I'm gonna do green this time. Where am I looking for my mins? What do my local mins look like? They look like Laredo, the valley, right? Okay, so 60. I'm a little bit above 60. What would you say that is? 62, 65, somewhere in that range. So your maxes look like the peaks, your mins look like the valleys. This one is what, 72 or something? I don't know. They're making me guess too much on this thing, I feel like. Their graph isn't big enough or clear enough. But you might have something like this in your homework, because I know they don't always give you something that's even Steven, sort of like I can just look at it. You might have to guess the number between a little bit. As long as you're picking something reasonable and not something that's out of that range, I'll give you credit for it. I'm not trying to like roll with an iron fist. It's like you're a fraction of a millimeter off on here. That's 63 instead of 62 now. Are there any questions about this? How to find absolute max, absolute min? So absolute max, absolute min, we look at the whole thing. We can take endpoints. We can take anything on this graph that we want. We're just looking how high, how low does it go, right? Locals, the local ones, I think the best way to get at the local ones is just think valleys and peaks. Anytime there's a peak, that is going to be a local max. Anytime there's a valley in that thing, that is going to be a local min. So we don't look at endpoints, but we look at valleys and peaks. For what X value was the temperature increasing? Or X values? Okay. So how many increases do you see in this thing? That might be a good question.
2.
I barely heard you.
2.
there's two of them, right? And so I'm hoping you see like this thing right in here and this thing right in here is an increase. From here to here, is the first thing I need to figure out. And then from here, here's the second thing. So I want this part and this part. How do I talk about that? And they're not even numbers, right? So if you just get close to it. Where am I starting? What number do I start with?
1.5.
1.5, what does that go to?
Like 2.75.
Yeah, that's good enough. So it's going from 1.5 to 2.75. And we talked a little bit about it, but if I'm doing intervals of increase, I don't typically include my endpoints. So that gives me that first interval. If I want to include another thing, you gotta put a little union sign in there. And now I'm starting my other interval. So where's my other interval going from? Where is it starting?
$3.75.
Is it? I think is that one right on the thing? That one's right on the 4, but maybe I'm wrong.
That's about right. 3.75.
It's about 3.75. It's hard to see because I already drew dots on my little paper. I'll give you a 3.75 or 4, right around there. And it's going to
5.
5 is good enough. And so this is my interval of increase. Are there any questions about this? So I feel like the first two parts were kind of like what we've been doing. This is like what we've been more active in. That last part was a bit of a review of stuff that we did a while back, right? So you still have to know how to write your intervals and still have to know like intervals of increase and how to write those sorts of things. Okay. All right, so another temperature problem. Did they really do like negative time on this thing? They kind of did, didn't they? They did negative months on this if you look at it. They start in July as their 0, which I guess is a.
I thought that was weird too. Anyway, but it's talking about temperatures.
July. I guess they want to go.
They're matching the temperatures.
They're starting in January, February, March,
Uh-huh.
and December. So they are starting at the beginning of the year. But for some reason, they're moving the axis like in the middle instead of.
I know it's weird to me because shouldn't June and July match? And instead they
But
have,
we also rant in this class. You really shouldn't have negative time, and then I was
yeah,
going to throw something in the negative time. But we'll go over it. We can still do it. The graph approximates the monthly average temperature in degrees Fahrenheit in Austin, Texas. Maybe that's why it's backwards. We're in Austin. And this graph X
Right.
represents the month where X equals 0 corresponds to July. Is this graph an odd or even function? So this is going off of symmetry. How do you know if it's odd or even? Is it odd or even? And how do you know?
Even?
It's gotta be even. Why do you say it's even?
All of the y values are equal across the equivalent or the opposite x values.
Yep, folded over the y, it's going to be the same thing. It is symmetric about that y-axis. Anyway, what's the metric about that y-axis? June corresponds to x equals a -1 and August to x equals 1. The average temperature in June is 83. What is the average temperature in August? Oh man, really? That is something you could do. So what are they asking you? How do we know what it is in August? We go like, what are they saying? -1 here and go up, it's going to be 83. So if we go to a +1 and go up, what number should we get at?
83.
Should be the same exact number. What they're trying to get at here.
If we have an even graph.
At Austin, where it's 83 in August.
No, I mean, average temperature is in degrees Fahrenheit. This is a problem that you will only see in your math class. You will not see this in reality. This is like,
Yeah.
that's not that's not realistic at all. They're about 17 degrees too short or something, I think. Is July even the hottest month?
I think it's August,
Yeah, I think so.
usually.
August and September sometimes.
Yeah. So this is not the most realistic, but if you want, you can scratch off Austin and put Boston or something. I don't know. You can pretend like it's not Austin if it really bugs you, I guess. I don't know. It's bugging me, so let's pretend like it's Boston from now on. March corresponds to x equals a -4 and November to x equals 4 according to the graph. How do their average temperatures compare? So if this is even, what do we know about x equals -4 and x equals 4? What do we know about their y values or their temperatures? They're like asking the same question over and over again on this, to be honest. So if it feels like you're answering the same thing, you might be. If this is even, what do we know about these two things? They got to be.
They'll be the same.
They'll be the same.
So the temperature is the same.
Temperature same temp. Interpret what this type of symmetry implies about average temperatures in Austin. That's kind of a weird question, maybe. Yeah, I'm not sure exactly what they're looking for there, to be honest. What would you say, I guess, is what I'm interested in. What is your interpretation of what this means?
Which one is it? What are we looking at?
It is 111D on 4.1.
Oh, you know what I did? I just matched up the months.
Okay.
I was like, I guess I put February is the same as December, March is the same as November.
Yeah, I don't know if they're saying that. Maybe I was thinking maybe they're saying like we're gaining heat as much as we're losing heat is what I was thinking.
Maybe
like the rate that we get hotter is the same rate that we get.
maybe
colder.
so. Maybe so.
It's like kind of weird. It's like, okay, but I know it's not true. Pretty sure, but that's what this graph implies. I don't know. If you want to log out and like log back in, I will watch for you if you want. Okay. Did you do that? He went. Okay. So I think Michael might be coming back in a second.
Okay.
My problems. Okay, so I think that's the end of this one. So that I think is the final problem in 4.1. Hopefully, that's all I got printed out. So there are a few problems we will get started on in 4.2. So 4.2, we start talking about larger order polynomials. So they start asking about turning points, x-intercepts. Let me total mod, look at it. And talking about the minimum degree versus turning points and those relationships. So hopefully you watch the video, and then we're going to match like a few symbolic equations to what their graphical representation might look like.
Can you hear me now?
Yeah, I can hear you.
Okay, sorry, I had a problem here.
And so this section we did higher order polynomials, and then the other thing we did was do piecewise functions. So we're getting into more sort of like more complicated piecewise functions. So we have done piecewise functions before, but now we're throwing things like squares into them, right? So they get a little more complicated. The little piece of it gets a little more complicated. Still the same sort of concept before when we did piecewise. So there's some more word problems. So it says use the graph of the polynomial function f to complete the following. Determine the number of turning points, estimate any x-intercept, state whether a is greater than 0 or less than 0. Determine the minimum degree of f. So there are 3 things they're looking at. Well, actually 4 because a is a 2-parter, huh? Determine the number of turning points. Oh man. So if this seems like a silly question, it might be a little bit. How many turning points does a line have? And like you can compare and contrast if you want. These have a few turning points. This one has how many?
0.
It has 0 turning points. It has none. And what are my x-intercepts?
Uh, 0.5.
Yeah, about 0.5. And so this is where you would probably want to write the point. So anytime I talk about an x-intercept, it is usually talking about the point. Right. Okay, so that's A, B, and C. So B says state whether the leading coefficient is positive or negative. So whether A is positive or A is negative. Typically, when I start doing things, I hope you realize like this is a line. This should look like something like mx plus b, right? When we talk about a line, it should have that linear equation. So there is a sort of like, what do I want to say, like variable scheme that they kind of do when we talk about higher order variables that I should probably talk about. They like to go like ax plus b, and then we go to like what quadratic is the next largest thing, ax squared plus b. They have this sort of like lettering schema, I guess, right? They like to go with the ABCs is basically what they do. Things alphabetically in your coefficient. It's just always going to be A, basically. A little bit. There we go. And so we'll just add another letter each time to represent. Right, we just add like a new letter each time to represent sort of like our constant. But that's the sort of like lettering schema they do with their variables. A, B, C, D, like your alphabet's always going to be like some real coefficient that's on that thing. With that said, if I want to think about my leading coefficient here, my leading coefficient on a linear function or a line is sort of like what? What does that represent? And I changed it from something else, right? What other variable could I put here? Y equals what x plus b?
MX.
Mx plus b, where m is your slope, right? So basically what they're asking when they talk about a line and its leading term, whether it's positive or negative, they're asking, is that slope positive or negative? So it's asking this the same thing, right? So is the slope positive or negative?
This one should be positive.
It should definitely be positive because it goes up left to right. And I maybe gave this away, but what is the minimum degree that you're going to have to graph this thing?
One.
It is the first degree. So this is at least a first degree. It could technically maybe be more, but I probably not, because if it's a higher degree, like a third or something, you'd probably see a little bit of squiggle in there. But it could technically maybe be more. Another way that we get to the degree is how did I get to the degree in the notes? Do you remember that? It relates back to this thing, right?
Turning points plus 1.
Turning points plus 1. 1 degree, and this is a minimum, right? At least. And so we go like one way, we say it's at least 1 degree, but and then they go the other way as well, right? If we have a 1 degree, it has at most 0 turning points. So they kind of go both ways with that property between turning points and degrees. So this degree could be higher, right? But this degree can't be any lower. Is kind of what it says. Are there any questions over this one? It's a straight line that doesn't turn at all. The x-intercept is what? Half comma 0. If we look at the leading term, let's do a quick recap. The picture that I want, and this was the end behavior thing, right? So it might do things in the middle. So they put a little box in the middle. But the picture I want in my head for this thing, if it's an odd function, what graph do I want to think about? That. What's the like smallest odd number that you can think of?
1.
The 1. So this is a first degree. If it's a linear equation, right? Something like that. If my a is positive, if my a is negative, this thing is going to go. So if you want to make a big black box in the middle, we don't care how it swiggles in the middle, right? If we're talking about end behavior. So in behavior, we're getting from that leading coefficient, or vice versa, right? We're taking this in behavior and we're determining that leading coefficient. So if we have an odd degree function, I want to think about a line. If I have an even degree function, what's the picture you should think about? What's like even degree? I know 0 is even, but it's not a good one to do. So don't do that. The next number after 0 that is even is deuce deuce.
2.
And so what does that picture make? What's a second degree?
Parabola.
It's a parabola. So this thing is like a parabola. So if it's a positive parabola, or if the leading coefficient on your parabola is positive, right? It's going to go an upright parabola. If it's not positive, if we have a negative parabola, that's a flipped parabola. Frowny face. This is what the end behavior of an even degree function what a positive and negative leading coefficient is going to look like. Right, they put little black boxes on whatever. We don't know what it's going to do in the middle, but out on the ends, this one's going to go up and up, and this one's going to go down and down going out, all right? This one's going to go down and up. This one's going to go up and down. When we go left and right all the way, we're talking about that end behavior, like what happens as we go out all the way right, what happens as we go all the way left. We don't care so much what happens in the middle. There's going to be a bunch of squigglies. Questions about like this sort of picture. So I'm hoping this is what you have in your head when we start looking at these things. A, B, C. So A asks about the number of turning points. So how many turning points are on this guy?
Which one? 5?
Yeah, number 5.
3?
Yeah, Hobie Luke and there.
Those are my turning points. There are 3 turning points. Okay. What are my x-intercepts?
You want like the points on the graph?
You can give me the X value. I'll fill in the rest if you want.
Oh, it's kind of weird looking. So what is that? Like a 6? I guess negative 6 is the first.
2, 4.
Oh, that is it. Yeah. 6, 0 would be one of them.
I think it's where?
1.
Minus 1. So
Yeah,
that
minus
it does hit the axis there. We're gonna assume it hits the axis.
Mhm.
And then the last one looks like right. I'm running out of room on my paper.
Yeah.
But it's there, right there, right? We're looking along, just to recap, I'm looking where it hits the x-axis. So we want to come along the x-axis and see everywhere it intersects it. That might be a good strategy to do. Put a little dot everywhere. I'm talking about those 3 points right there. So for turning points, I'm looking at like those peaks and valleys. Where does it go from up to down and from down to up? For these, I look where it crosses the x-axis. Those are my x-intercepts. Part B asks about the leading term. So is my leading term positive or negative here, and how do you know?
Negative.
Is this an odd degree or an even degree function?
Even.
It's even. So what we're thinking when we think about even, like this picture in your head, right? Think about even. The first thing that should pop in your head is this should look like a parabola. So now I'm looking, does this look like my parabola is going up or down? So this looks sort of like a parabola. It's got some squigglies in the middle, but if I just smooth them out, right? That looks like a parabola. Is that a positive or negative parabola if I'm looking at that end behavior? And Hunter already said it, but that is like a negative parabola. It is shooting off towards negative. Any questions about that? Any other way y'all want me to go through that? I could try some other way. But I'm hoping these pictures like get ingrained into your brain somehow, right? It looks like a line or it looks like a parabola. That's kind of the best way to simplify this, right? The end behavior on these things. It's either odd, the highest degree is either an odd degree or the highest degree is either an even degree. Okay, and the last question was what? Determine the minimum degree. So there are a few things that indicate that we need probably this degree. The first thing that I would probably point out is we have 3 turning points. So based off of 3 turning points, what can I say the minimum degree is?
Well, it's +1, right? So that's 4.
Ooh, yeah, +1.
We haven't gone over the zeros yet, really. But we did go over the zeros with like quadratic. We hadn't gone over them with higher degree polynomials. But you might notice you're getting 3 solutions. So this indicates it would need to be at least a degree 3. We know it's an even, so we'd probably have to bump it up to 4. There's something with the way this one hits the axis and turns back around that we'll get into in the next chapter that makes it like a multiples there, but you should be getting what, 4 solutions, right? Is what we're indicating with degree 4. At most 4 solutions, I guess I should say, right? We can get less. And we can get less through things being like multiples, right? Oh, so 7, ooh, almost running off the page. 7, we want to do ABC again. So A asks about turning points. How many turning points are on this guy?
Four?
How many? There's 1. I didn't hear what you said. Maybe I heard wrong. I don't know.
I think she said 4.
She said 4. I couldn't hear if she said 1 or 4. I was like, I'm not sure if I heard that right. Okay, so there are absolutely 4 turning points. Okay. Where are my x-intercepts? So my best advice is to probably go along here. Put them in. I think there's going to be 1, 2, 3, 4, 5 times that thing hits the x-axis. -1, -2. Where does it start? What's the first x value?
-3.
-3 looks like the first one. That -1? I am going to that -1. What is this one? 0, 0. That's the origin. Looks like 1, 0 and 2, 0. I think are my other 2 numbers. And I'm picking off of that x-axis. Okay. So part B asks, what about the leading term? So based on the in behavior here, is this an odd or even degree function?
Odd.
It is odd. And does this, once you think about that, does this look like a line going up or a line going down based on just the endpoints, the ends out there?
Line going up.
It definitely looks like a line going up. It's shooting down as we go left. It's shooting up as we go right. So if it's a line going up, our leading coefficient or the slope would be positive. So line going up, line going down, parabola going up, parabola going down. There's the pictures you want in your head, right? Ask about what, the degree of the function. What's the minimum degree here? And there's this one really reinforces it, I think. Probably better than the previous one. I want to do what?
Add 1.
Add 1 to that guy. So there is at least a degree 5, right? Another thing that might indicate you're getting a degree 5 is we got what? 1, 2, 3, 4, 5 different values for our x. That might have something to do with each other. Okay. Any questions over this one? How to count turning points? I think that I'm hoping that's something that's straightforward. If not, definitely stop me. So we count peaks and valleys basically to count turning points. If we want x-intercepts, we look at where it goes to the x-axis. If we want the degree, it's our turning points plus 1.
Add on the next problems, I realized as I was working through these,
You didn't
I
put the graph
forgot to
on
put
there?
the
Yeah, I
graphs
got
on
'em.
them. Oh, good, good, good. I emailed them to everybody and I did put them in Blackboard. So if you want those, they're
I
there.
think this might close out this lesson today because you get 6 graphs here. So we want to match the equation A through F with one of these 6 graphs. We want to identify the turning point. We want to estimate the x-intercept. We want to estimate any local extrema and absolute. Any more? Can I get them all in there at once? Probably not. It's too many. Maybe, kind of, sort of. So we're looking at these graphs, we're looking at these equations. So I think the first thing is probably to match up the graph with the equation. I think it might be easier to do it on this paper, if I'm being honest. So if I'm looking at these equations, 1 minus 2x plus x squared, I think the important thing to do is to look at the degree of the function. So if I'm looking at 15, what is the degree of my function there?
I would say 2.
Yeah, it's a degree 2, so it should look like a parabola, right? What about on 16? That's a degree.
I can't read because it's kind of hard. Is that a cubed?
It's like, yeah, it's, let me try to zoom in maybe a little bit.
Is that
Trying to get
cubed?
everything in there at once, right? And yeah, 3x
If
minus
you
x.
check your email, it's on there too. So
Oh. Sorry.
Yeah, so that's a cube. That's a cube. This one and this one both look like they are to the 4th power. So this one starts out with the squared. You might have to rewrite number 19 in descending order. Same thing with 16, right? It doesn't start out with the cube, but you might want to rewrite that in descending order. So that might be the first thing you want to do is actually write these things in descending order. It might actually help you determine what they look like a little bit better. Same thing with this one. This one's not in descending order either, right? X squared minus 2x plus 1. I think that guy and that guy are in descending order. So it looks like I have one squared graph. Can you guess where that square graph is going to go, or that quadratic? We get 6 different pictures. Which one of those is it going to be? That one I think sticks out kind of like a sore thumb in these pictures, probably.
Yeah, it should be graph D.
D right there. So this one is my 1 minus 2x plus x squared. Minus x plus x squared. So we got 15 accounted for. So now we're looking at these other, what, four of them. So now I want to look at my cubics. I think that might be the next best thing to look at. I'm looking at these 2 cubics. Ooh, these next 2 are cubics. What do you notice might be different between the 2? There's one thing you should really look at here.
One's negative and one's positive.
Yeah, so this has a negative leading coefficient, and this has a positive leading coefficient. So back to talking about end behavior, what does the end behavior of these things look like? That's what we really need to think about. So we're either thinking about a line or we're thinking about a quadratic. Which one should we think about?
Line.
A line. So this one looks like a line going down. This one would look like a line going up. And they are cubic. Can we find one cubic going up and one cubic going down? So how many turning points at most should a cubic have? So degree 3 should have
2.
2 turning points. So we're going the other way. We subtract 1 to get to our turning points. So we're looking at something that has a positive line behavior. We're looking at something that has a negative line behavior. We already did that one. So I think we're focusing on probably those two right there. So what should B be? Would that be 16 or 17? I think we're narrowing it down to these two, is from what I've said, right? 2 turning points would be these two. B would be
Number 17.
number 17. That would be the positive one. This would be 17, which would make this what? 8, 16. Sorry, I skipped 16. X equals, where am I at? 17 was x to the third, 3x squared minus 9x. And 16 said something like x equals minus x to the third plus 3x, when I rewrote it. Okay. And I think we have 2 that are to the 4th degree, right? So we get an x to the 4th minus x 8x squared. And then 19 looks like a negative x to the 4th plus 8x squared. So we don't have too many graphs left over. I think we have A and E, right? Or F, sorry. A, E, and F. Ooh. Did they give us, I guess they give us an extra graph in here, huh?
Yeah.
Okay.
Did they? I only have 6 graphs.
Yeah, and there's 5 equations. Unless I'm missing something.
I have 6. 15 through 20.
I'm missing 20 then, apparently.
Oh, yeah. Because
Whoops.
20 wasn't actually on the,
On the numbers.
yeah, actually it was only the odd ones, but it's 15, 17, and 19.
Okay, so we're looking at 18 and 19. And they are both quartic functions. What does the end behavior look like on those? Am I thinking parabola or am I thinking straight line? And how do you know? So I'm looking at something that is a degree 4. How do I know what that looks like?
Double parabola.
It's going to look like a parabola, right? And so this one I think is going to look like a positive parabola. This one should look like a negative parabola. So based on that, we've got this picture, and this picture. Can you guess which one is it not going to be? Like right off the bat. Which one doesn't look like a parabola at all?
E.
This one, right? So right away, I think this should have been probably question 20. Right? Okay, so now we're looking at 18 and 19. Which of these looks like the positive parabola? So 18 would be like the positive parabola. Which one would that be? A or F?
F.
F, absolutely. So 18 would be this one. Equals x to the 4th minus 8x squared. And then this one by the power of deduction. I figure out that's the other one we hadn't talked about yet. Minus x to the 4th plus 8x squared. Okay. So matching these things was the first sort of step here. And this was what, number 19? A, I believe. Okay, so now let's look at A. I think just looking at the graph and going the graphs in order probably makes a little more sense than trying to do them in order of whatever the heck they're doing. B asks for identify the turning points. So how many turning points does this thing have? I'm hoping you're looking no longer at those points.
So 3 turning points.
There should be 3 turning points. They want you to list them here, I think, is what they're saying. Identify the turning points. So we want to look at the point. This is -2, 16, I think is what they're wanting here. The other one is what? And what?
0, 0.
0, 0, and 216. Yeah, that's it. Estimate the x-intercepts. So what would your x-intercepts? And these are turning points.
-3, 0, and 3.
Any other ones?
Yeah, 0, right? The origin.
Oh, you said 0. Okay, I got confused. I thought you were saying
Sorry.
point and you're giving me a number. Sorry. Ooh, gotcha. It also goes through the origin. These are my x-intercepts. Absolutely. Part D says estimate any local extrema. So there's actually like four things in these last 2 questions, I think. There's like a local max. Anytime they say extrema, you better tell me local max, local min. Even if it doesn't have one, I know that it doesn't have one. So do I have a local max anywhere here? And this, remember, we're just talking about the y value for these things.
16.
16 is my local max. Do I have a local min here? Ooh, this is a good one. Do I have a local min?
Yeah, 0.
0. Okay. I didn't hear. I didn't hear you just said it. Okay.
So the extrema will refer to both local and absolute values.
Extrema means both max and min. When they say local extrema, they mean both the max and min.
Oh, local extrema. Okay. I'm still trying to sort out the terminology here.
Yeah.
So when we're told about extrema, we would either be told local or absolute extrema, right?
Yes, yes. They have to specify which one they mean.
Okay.
So there's local where we talk about the valleys and peaks, or yeah, and then there's the absolute. So if we want the absolute max, is there an absolute max on this guy? And if it is so, what is it?
It's the same thing because, you know, 16.
16 doesn't go any above that. What about my min?
Because of the arrows, it can't go any further than 0.
Yeah, so
Oh, so it's none. Okay.
None.
I see. I keep on making that mistake.
yeah, so okay. So this we want to go, how far down does this go? If you tell me 0, I can go to -1 in my graph, right? So I can go down further. I can keep giving. The arrow means that I can keep giving you something lower.
Okay, so but the absolute max isn't affected because the arrows are going down and not up. Correct?
Yes, yes, they're going down. If we had an arrow going up, we wouldn't have a max.
Then we wouldn't have a max.
Absolute.
Okay, okay.
Yep, yep. Absolute, we just look absolutely. We look at everything and anything that's here, right? We don't care so much where it is, whether it's a valley peak or whatever.
What I don't understand is why you can't put infinity as an answer, because you figure we've used infinity so far
So
in
minimum,
the math.
when
so-
you're talking about a minimum, you're talking about a value that you can give that you can go no lower than. And so
Mhm.
if you give infinity, infinity is not actually a number, it's a concept that you can't actually reach.
Mhm.
So if you said infinity, it would be almost like you're using infinity as a number, and you really shouldn't be doing that, if that makes sense.
Mhm.
It's like, give me a number and you tell me infinity. Like infinity itself isn't a number, it's a concept of going and keeping going.
Mhm.
Yeah. And it is a bit confusing because when we talk about intervals and stuff, right, we absolutely use infinity, right? If I go from like minus infinity, but there's also the reason like we don't ever include infinity, right? Because we can't use infinity as a number, it's a concept. And it's a really weird thing, right? And this is like why math is literally like one of the best things out there. We get to talk about infinity. We get to talk about different sizes of infinity. Like, what the heck isn't? Go ask the man on the street. Like, what is infinity? See what he says, right? I don't know. It's a crazy concept. I don't know how else to say it. Like, I've studied it a good portion of my life. It's still crazy. And it's not something that's super intuitive all the time, right? Makes you think. Makes me think. So I'm just projecting that. Okay, so A, we figured out what was number 19. We figured out the turning points. We figured out the x-intercept. We figured out local min and max. We figured out absolute min and max. Any questions about any of these things or how to figure them out? So like I'm hoping, like it might take you a second, but like I'm hoping it doesn't take you a lot longer than that. These things, I think you kind of like either know what we're talking about or not. There might be a little bit of formatting issue. I'm not trying to negate that. Okay, so doing part B. So going again for part B, we want turning points. So what are my turning points? I think there's 2 on this one. So what are my
-3 and like 20.
20,
A little bit above 25, but
27.5 something? So 25. It is a little bit over 25. Sorry. And the other one is where 1 and
-5.
I think that one is actually hitting it, right? So these are my turning points. Okay, and then the next thing I want to do is my x-intercepts. I'm looking at my x-intercepts. What does that look like? I think that's what, a -5, 0, 0, 0. I'm not sure what, like some of y'all are really quiet and some of y'all are really getting this. And I'm afraid some of those that are really quiet are maybe just like tuning out or something and just like giving up or something. Like, I hope it's not the case. It's like we're kind of doing the same thing over and over again. So I'm hoping you are picking it up a little bit. But those are my turning points. These are my x-intercepts. The extrema might be something I'll slow down a little bit on. So local max. What is my local min? Do I have a local min on this thing?
Yes. -5.
The -5 is my local min. Do I have a local max on this thing?
27.5.
That's that nasty 27.5 up there that we guessed. I think I swapped these. Min, max, max, min or something. But as long as we get them both on there, I think they should be all right. Do I have an absolute max? What is my absolute max? Do I have one?
No.
No. Why? Because of this arrow going up, right? So this arrow keeps going up. There is no absolute max. Is there an absolute min?
Also no.
Also no. None and none. I think it might be safe to say, I might be wrong. There might be a counterexample, but as long as it's going like up and down and there's a valley and a peak, there should be local maxes and mins as long as we're getting valleys and peaks. As far as absolute max and min, we can't make that assumption, right? Okay, so that's what A, B, C. Let's look at C. It is 10:20 right now. If you need to get going places, you can go ahead and do that.
And I'll post everything up till now on the,
All right. Did you want me to finish up these last like 4?
yeah, if you, yeah, sure.
Okay, we'll do that real quick because these
Oh,
are.
or I'll do it tomorrow. I mean, we can do it tomorrow, whatever you want to do.
If you want to do like maybe I'll do this one at least. Did you want to do these 3 or these 2? There's like 2 of them.
Yeah,
Match the graph. All right, I'll finish up this one and then I guess we can finish up those other 2.
Okay.
Next class. All right, so part B. Identify the turning points. I think there's 2 turning points here.
so are we stopping on 18?
So I did them kind of out of order. We need to do 15.
Oh, okay.
We need to do number 15 and number 18. I think.
Got
what
it.
we're doing. Yeah.
And then where do I start tomorrow?
Just here doing 15, 18, and then jumping to 55 and all that good stuff.
Oh, gotcha. Okay.
So it's just like these 2 graphs are the 2 that we have left after this one. I did them out of order. I did them in the order of the graphs.
Okay.
That's what I
Okay.
did.
Yeah, I was just kind of, yeah.
It should be graph D and F is what we need to go over after this.
Okay.
So I want to pick out my turning points from this thing. I don't want to spend too much time, but -1 is where it's going through on my X. I think -2 is where it's going through on my Y. So that is at a -1, -2. This one should be at a +1, +2, I believe. And so I'm picking off these 2 points from my graph. These are my turning points. Part C says, what are my hex intercepts? So I'm looking along here. Oh, that is ugly because it's not quite 2, right? Whatever. So not quite 2 over there. Is probably the first one at a negative not quite 2. Or is also known as -1.9. The origin looks like it's symmetric, so it looks like it's at the positive of the other end. So not quite 2 on the positive end. So that is C. D says local max, local min, absolute max, and absolute min. So what is my local max here?
2.
It should be that 2 at that peak. My local min here is
-2.
yeah, -2. What about my absolutes? Do I have an absolute max?
No.
Got an absolute min?
Nope.
Any questions about this? Okay. We got a few problems to figure out next time. Gonna have to do some piecewise functions.
Test is still for the 11th, right? Correct?
Yes.
Yeah.
Okay.
I know. Okay. Yeah. Try to do too much math in my head at one time. 11th is next Wednesday. That's it.